Hello students, this problem we're going to compute the Laplacian of this scalar function here. Notice that there are spatial components, x and y, and a temporal component, t. So I'm going to think of it in terms of those physical interpretations. T is time, and the x and y are the spatial components. That'll help us with the mechanics of computing the Laplacian. Okay, so in this video we're just going to go through the mechanics of computing the Laplacian, just straight from definition. All right, so the Laplacian is defined as the gradient operator dotted with the gradient of the function, or is the div of the gradient of f. So that is a dot product of this gradient term here dotted with the gradient of f. So remember, when you take a dot product, you get a scalar function. So the result of the Laplacian will be a scalar. A lot of times the Laplacian is denoted as del squared or nabla squared. It's the grad squared of f. It's a second derivative operator. Okay, so let's apply that definition to this function. But first off, I want you to note that there is no time component in the Laplacian. It is completely spatial. We'll only be computing the spatial derivatives. We will not be taking the second derivative with respect to t. Okay, a more efficient and compact way to write the Laplacian is if you dot this ddx, if you dot this gradient, sorry, with the gradient of f, then you are taking ddx and you're going to apply it to df dx, and you're going to get d squared dx squared plus, because of the dot operator, d dy applied to d df, so you'll have d squared f dy squared. So it's the second derivative in the x component plus the second derivative in the y component. All right, so now we are going to apply that operator. So that means I take the second derivative of f plus with respect to x, and I take the second derivative of f with respect to y. So since the e to the minus 5 pi t has is ignored by the spatial derivatives, I can just factor that out, and then I will simply take the derivative of the x component in this first term of the summand, and I'll take the derivative of the y component in this second term of the summand. So when I take the derivative of sine, I get a cosine, and a pi pops out for the chain rule. And when I take the derivative of sine, I get a cosine, and a pi pops out from the chain rule. Then I apply the derivative again, so this would be the second derivative. So the second derivative of sine gives us a sine back again, but I get a minus because the derivative of cosine is minus, and the pi pops out again, and I get a minus pi squared. Similarly here, I take the derivative of cosine, I get a minus sine, and then the pi pops out because of the chain rule, so I get a pi squared. Now you notice that these terms are like terms, so I can add them together, and I can simplify this expression. So I have a minus 2 pi squared e to the minus 5 pi t, which was untouched by the Laplacian, and I end up with the sine pi x sine pi y. Now you'll notice that minus 2 pi squared is multiplied by the original function. If you look at the original function f, our solution here, or our computation of the Laplacian of f, gives us the function back again. And so you notice that that is f of x. And this is similar to, you've seen this before in linear algebra when you've looked at eigenvectors. Remember, when you applied a matrix to an eigenvector, you got the vector back again multiplied by a scalar. The same thing applies to functions. This function sine pi x sine pi y is an eigenfunction of the Laplacian operator, and the eigenvalue in this case is minus 2 pi squared. So for those of you going on to take things like partial differential equations, this becomes very important when we are solving those types of equations. All right, good luck.